So let's see example 5.1. So here GL is given is 200 ohm minus J 100 ohm, and then this problem example asks to design matching circuit to transform to GL to G0 is 100 ohm, right? So if we have some circuit 200 J100 ohm, we have transmission line is 100 ohm, so it asks design matching circuit here, matching circuit. So to use Smith chart, we can do normalize impedance, right? So 2 minus J ohm. So in Smith chart, this is a R1 circle. So 2 means maybe over here, higher impedance. And then 1J is minus 1J is here, right? This circle, R2 circle, and then X is minus 1 circle. Here is a intersection, right? So this is a normalized GL. So from here, how can he move this position to origin? So because this one is R1 circle, right? So this position inside R1 circle, series 1, even though if we use series L and C, we don't have any chance to move this origin position. Only thing we need to do is shunt component, right? So draw a line with the constant G circle which intersect this position, this GL position. This is constant G circle. So if we move from here to here, right? So what is this? This is a shunt L. And if we go down, we can reach to this origin, right? So shunt L, then this is series C. So number one topology can be, let's say this, let's put this as 2. So shunt L first, so GL, shunt L first, and series C later. So this is the second option. And then another one is from here we can move down, right? So what is this? This is a shunt C. Stop at this R1 position. We can move up to this way. So what is this? This is a series L. So let's say this is topology 1. So from this GL, we connect shunt C first, and then we can connect series L. This is LC. So we have two option, right? So the problem asks if the frequency is 500 megahertz, 500 times 10 to the 6. Then what is a C and L value? What is L and C value for topology 1 and topology 2? So if you get this value without any problem with using this Smith chart, that should be good. So this is the purpose of this kind of L matching. So let us start from the option 1. So this topology 1 first. So let's locate GL in this Smith chart. So normalized GL is here, right? So 2 minus J. So if you find two resistance circle, this two, right? Start from here, and this is reactance is minus 1 circle. So this is position of normalized GL, right? And then so let's connect L is 2 minus J, because we need to, as I showed, we should move to this one. So this is a this circle. This circle is constant G circle, right? Because we use a shunt value, shunt C first, we follow this constant G circle, right? So we move here to this position, but we should stop at this R1 circle. So it's not easy to see. This circle. This is R1 circle, right? So this is R1 circle. So we basically start from here and move to this R1 circle, shunt C, and then move to this one, series L, right? So what you need to do is, from this GL, is start from shunt C. So we need to know the position over here to understand what is admittance value, susceptance value required from the C. So if we convert this GL to YL, so let's read this value, this kind of admittance scale. So this position provide 0.4 G, right? This one is 0.2. So YL is 0.4 plus J 0.2. And then we stop this position, right? We stop this position. So if we read the admittance here, so this is 0.5, right? So after we connect this capacitance, this Y, normalized Y become, because we have a constant G circle, G is same, but susceptance changes, right? So 0.4 plus J 0.5. We have 0.5 here, right? So because of this C, so let's say this is Y cap. So Y cap is contribution is 0.3 J 0.3, right? The susceptance. So basically this shunt C add 0.3 J from here to here, right? So this is a difference. And after that we have a series L. So series L we can connect here. And then finally this one become 1, right? So 1 is here. 1 is here, right? G in one position is here. So the difference from here to here, right? So if we convert this one to J 0.4 plus J05, so if we read impedance value from this position, so this value is 1 and then minus 1.2. So here, if we read impedance value from this, so Y is 1 minus J 1.2, right? So by moving from here to here, this inductance increase plus J 1.2, right? So if you say L, see this is L. So because normalized G from inductance is J 1.2, right? Because of L add 1.2 plus 1.2 J, that's why we finally this become 1, right? So from here we get the value for Y cap and G inductance. So from this value, so Y cap is J 1.3. So Y capacitance is J omega C, as you know from the circuit course. So Y cap normalize J omega C divided by Y0. This is same as 0, right? So Y0 is 1 over J naught. So this value become J 0.3. So C can be 0.3 omega G0. So here G0 is 100 ohm, omega is 2 pi 500 10 to the 6, right? So if we plug the value, the capacitance 0.95 picofarad. Pico means 10 to the minus 12 farad, right? So this is how we get this capacitance value. And then G in inductance, we calculate J 1.2, right? So G inductance normally is J omega L. So normalized G inductance is J omega L divided by G0. This becomes J 1.2. So L become 1.2 times G0 divided by omega. So L become 30.2 nano Henry, which is 10 to the minus 9 Henry. So we found that, right? So GL is given. If I have C and L with this value, this GL become normalized GL is 1, which means G in is 1, which means G in becomes G0. So it's matched to G0 transmission line. So here this impedance is G1, right? So because G0 is matched, so there will be no reflection here. There's no reflection. 0, right? So this is the matching circuit we design for the impedance matching between GL to G0. And then about this, let's see the second topology here. Second topology here, right? So this is opposite way. So it start from shunt L. So it move up and down. So